Determine if the sequence converges or diverges. If it converges, determine its limit. All we have to do is find the limit as n approaches to infinity of an. That is n approaches to infinity of e raised to negative 3 over root n. Now we can move this limit to the exponent. E raised to limit n approaches to infinity of negative 3 over root n. That's exponent. That is, on the exponent, when n is very big, negative 3 over very big become very small. That's very close to 0. So e raised to 0, and a number raised to 0 is 1. That means this sequence converges and the limit is 1. Next, we got negative 1 to the n. So negative 1 to the n is, in fact, when we take n equals 1, 2, 3, 4, etc., we get negative 1, 1, negative 1, 1, etc. Okay, so we can use the fact that when we have a sequence, and when we take absolute value of the sequence and take the limit when n goes to infinity, if it goes to 0, then if this happens, then limit of an as n approaches to infinity is also 0. So how does this help here? Because when we got negative 1 to the n or n plus 1, and when we take absolute value, it's going to be all positive ones. 1, 1, 1. So this will be just 1. And we know how to take the limit after we get that. Okay, so let's find the limit of absolute value here. So limit as n approaches to infinity of absolute value of this. Okay, so that is same as limit n going to infinity of, let's find the absolute value. On the bottom, 5 square root of n, both positive, so absolute value of positive numbers are always positive. On the top, negative 1 to the n, when we take absolute value, it's going to be just positive 1. Without absolute value, it could be negative 1, 1, negative 1, 1, but when we take absolute value, it's always 1. And this limit is, since n goes to infinity, the bottom becomes really big, 1 over really big is 0. So since absolute value of this sequence, the limit of the absolute value is 0, that means limit of this sequence without absolute value is also 0. That means this sequence converges and the limit is 0. So next question, let's find the limit of n square over n cube plus 7n as n approaches to infinity. So when n goes to infinity, the top goes to infinity as well, because infinity is squared. On the bottom, square root of infinity is also infinity. It's like this, and we have no information about infinity over infinity. What we can do is just divide the top and bottom by, here is square root of n cube, that's the leading term. We can divide top and bottom by square root of n cube, or we can just divide by n square. N square means square root of n4. When n is positive, square root of n fourth power is n squared. Maybe let's do that. This works as well. Okay, so let me divide by n to the fourth on the top, and whole thing is square root of n to the fourth. Square root of n to the fourth is in fact n squared, and we can simplify this. If we simplify, we get limit n approaches to infinity of, this is n square over n square over n square, 1 on the top. On the bottom, square root of something divided by square root, so I can write whole square root for top and bottom, n cube over n to the fourth, so 1 over n. I'm separating this, n cube plus 7n over n to the fourth. N cube over n fourth is 1 over n plus 7n over n fourth, just 7 over 1 copy of n cancels, so n cubed. So we get this. Now let's take the limit. So on the top, this 1. On the bottom, when n goes to infinity, when n is very big, 1 over n is very small, 0. And when n goes to infinity, this is also 0. That means the bottom is kind of 0. This approaches to 0. And 1 over something really close to 0 is very, very big. That's infinity. That means limit does not exist. We can write dne. This is infinity, or dne. So this sequence diverges. Sequence diverges. And here is another. So let's take the limit of n squared e to the negative n. Let's get rid of this negative exponent. I can put on the bottom and do this. If you look at closely, n squared e raised to n, this exponential grows much faster than the top. When this grows faster, this becomes infinity faster. So something over infinity, very big, is 0. The answer is 0, but we need to justify that. What we can do is, like we've seen in calculus 1, we can use L'Hopital's rule. Okay, for that we need to convert these to real numbers. These n's are just the natural numbers, 1, 2, 3, 4, etc. But this one, it will be, we know it's 0. Why? I can justify in this way. Since limit of, let me put x squared over ex, when x going to infinity, this limit is, if I use L'Hopital's rule, this becomes limit x going to infinity of derivative of top on the top, derivative of bottom on the bottom. Okay, again plug in infinity, we get infinity over infinity. So L'Hopital's rule one more time, that gives derivative of 2x2, ex is ex. Now the top is a number and the bottom is still infinity. E raised to very big is very big, and 2 over very big is 0. Okay, since this is 0, and this works for integers as well. Or you can just say, okay, the n squared en, if we graph, this one grows faster. That means this becomes infinity faster than that, the whole thing is 0. Okay, and the last here, we know that natural log of x minus natural log of y, that is natural log of quotient. Okay, difference of two natural logs. So I'm going to use that property here and take the limit at the same time. This an is limit n going to infinity of natural log of difference, means natural log of quotient. Okay, just 3n squared plus 5 on the top, n squared plus 1 on the bottom. Now we can take this limit inside, so this is natural log of limit of n going to infinity of 3n squared 5 over n squared plus 1. Now if we find this limit inside, when n goes to infinity, we got n squared, same power. That means this limit is just 3 over, there is nothing means 1, just the ratio of leading coefficients. So 3 over 1, just 3. So the whole thing is now ln3. That means this sequence converges and the limit is ln3, final.